Here's a quick proof of Theorem 10, which is to bisect a given finite straight line. All right, so it's given this finite straight line, AB, and we must construct basically just a point D, which bisects AB. Okay. Now, in the modern way, we would just measure it. It's 1.5 inches, and half of 1.5 is like 3/4. So you just use the ruler to find that point right there. But of course, marks on rulers are not allowed in Euclidean construction. You have to use compass and straight edge. So the way this is done is we first draw equilateral triangle ABC, and that's Theorem 1. So I'm just gonna, without going through all the steps of that, which you all showed how to do it on the board, okay, I'm just gonna do the light version, which is I'm just gonna open and draw only the parts of the two circles that I need, which is I just need to find the point where they cross up there, and that's C. And then I'm going to draw AC and BC. And again, I don't have to cite postulate 1 or anything like that, because that's all written down in Theorem 1. All right, now I still don't have how I'm going to get the bisection point D. But here's how it's going to work. I am going to now bisect angle C. In fact, I'm going to call it angle ACB. ACB. And I know I can do that because I just proved it in Theorem 9. Okay, do you remember what Theorem 9 was? Bisect an angle. So I can pick a random point on this line. And you know what? I'm just going to be lazy and pick A. And I'm going to cut off the other line at B so that it equals, so that CA equals CB. Oh, wait a minute. CA and CB are already equal. Well, great. Now all I have to do is just draw another equilateral triangle on top of AB, or sorry, underneath AB. Hey, look at that. I haven't moved my compass at all. It's almost like I could have just drawn a vesica Pisces. But it's the way I'm thinking about it that's going to make it possible to prove that I can bisect this line. Okay, so that is, I don't need to name that point because all I really need to do is join that point to C, and boom. Wherever that line that I've drawn hits AB, that's going to be my point D. Okay, so bisecting ACB is going to be line CD. Okay, so where the intersection of the bisector line, bisector of ACB, is going to intersect, that upside down U again means intersect, wherever that intersects, line AB is going to be my point D. And I don't need a reason for that step. That's just a naming step. So now I'm going to write a proof that what I did accomplished what I said it was going to do, which is that D bisects AB. Okay. Point D bisects line AB. So that's what I want to prove. Wait, I'm just going to say title proof. So, but I have to also say what's given. What is given is the construction above. And again, I'm not going to repeat it because it's all written down right there already. So given the construction above, I need to prove that D bisects AB, that point D bisects AB. And the way I'm going to do it is congruent triangles. Okay, in order to prove that D bisects AB, I need to prove that AD equals BD. And the way I'm going to prove that is to prove these triangles congruent, ACD and BCD. However, I need to prove them congruent, not by the SSS, because I will never be able to prove these two congruent before I prove the triangles congruent. Only after using CPCTC. So where did this line come from? I constructed it, I conceived it as the bisector of ACB. So what do we know about these two angles? We know that those two angles are equal because I used Theorem 9 to bisect angle ACB. That guarantees that this line splits ACB into two equal parts. I just called them angle 1 and angle 2. So that is the definition of bisect. Okay, now I also know that AC and CB are equal. AC equals CB because they were conceived as the sides of equilateral triangle ABC. And so therefore the definition of equilateral triangle assures us that they are going to be equal. So we almost have the two triangles congruent. Click, click. All we need is a third click. The locker opens. We got AC equal to BC. We got angle 1 equal to angle 2. So in order to have side, angle, side, we need to show that CD in this triangle is equal to CD in this triangle. And indeed they are equal because they coincide. Axiom 4 says things that coincide are equal. That's an axiom known as the reflexive axiom. So you can also put reflexive on there instead of axiom 4, or instead of just saying axiom 4 is things that coincide are equal. All right, click, click, click. We heard the clicks, and ka-chunk, the locker opens up. As in the other proofs, these first three can be in any order. Order does not matter for the first three steps, but you may not do step 4 until you have all three of these steps logged in on your proof. So that's triangle ACD is congruent to triangle BCD. Make sure A lines up with A, C with C, and D with D. And that's not by the SSS, but rather by the SAS. That's super important that you know Theorem 10 is impossible without the SAS. All right, ka-chunk, the locker is opened. We reach in the locker. We grab the only prize that we need, which is angle 1 equals angle 2, CPCTC. And hence that proves what we want, which is that, oh, I'm so sorry. We had that already. That's not right. Mistake. All right, what I meant to say is that the prize that we want is the third pair of sides. AD congruent to BD, or equal to BD. That's what we wanted to show, and that is by CPCTC, and that proves that D bisects line AB, because bisection means cut it into two equal parts. And since we've shown it's cut into two equal parts, therefore, the definition of bisection says we've proven what we want. So we get to say QEF, quod erat faciendum, which means which was the thing we needed to do, or the thing we needed to make. We needed to make this bisector. And that's it.